So last week we have learned how to model the digital circuit in Verilog, or how to describe the digital circuit in Verilog. So basically we have three types of modeling style. The first one is data flow modeling, where we need to have the Boolean equation, in order to use data flow modeling. And we can use the assign keyword, in before we have the Boolean equation. So assign and followed by the Boolean equation, right? And also we call the assignment, as the continuous assignment statement. The term, the assigned keyword is the continuous assignment statement, and this is for data flow modeling. And also we learn how to describe the circuit using behavioral modeling, right? And also the structural modeling. So behavioral modeling, we need to describe using the behavior of the circuit, and also, of course, we need to use the always block. We write the description of the circuit, the behavior of the circuit in the always block. So for example, if we use if else statement, so that if else statement must be inside the always block. And also we have structural modeling, where we can describe or model our digital circuit also using the structure of the circuit, where we need to have, of course, the structure or the schematic of the circuit, because we describe the structure based on the connection of the circuit, what the gate that we have and how the gate is connected to each other, right? So that's it's called the structural modeling. The advantage of behavioral modeling as compared to data flow and structural modeling is that you don't need to have the Boolean equation. You don't need to have um, the schematic or structure of the circuit. So you just can straight away describe the circuit based on its behavior, right? So if you know what is the input and you know what is the output for the for the input combination, then you can create the Verilog code to describe the circuit already. Okay. So also, when you ask when to use uh, the data flow modeling, when to use the behavioral modeling, when to use the structural modeling, the answer is depend on what kind of circuit that you want to describe. So for small circuit, you can describe using data flow modeling, right? Because you can derive the Boolean equation, and also you can derive the schematic. Then you can use data flow and structural modeling. But if you have a very uh, a big circuit, all right, you have more than 10 input, for example. So to derive the Boolean equation for that kind of circuit is difficult. Okay, so behavioral modeling is the answer. Okay, so most of the time later on, when we design our circuit, we will use all the three modeling style in maybe in one design. Okay, so it's actually depend on what kind of circuit, and also the your experience. All right, if when you start to code, uh, start the Verilog coding, so you will build your skill in describing the circuit in Verilog. So later on, you will automatically know which modeling style that you need to use for a specific circuit, right? So in chapter 3, we will use a lot of this modeling style later on, right? So basically, in chapter 2, these are the things that you need to know, right, before we proceed to the uh, more advanced topic in chapter 3, 4, 5, 6, and so on, right? Okay, so now today we are in chapter 3. Chapter 3 is for the combinational circuit design, and these are the chapter outline. We will have multiplexer, decoder and encoder, adders, subtractor, comparator, multiplier. These adder, subtractor, comparator, multiplier are the arithmetic circuit where it is very important in digital system, especially in computer, right? Where we use this kind of circuit for computing, right? To do the arithmetic. And lastly, we will look at the design of ALU or arithmetic logic unit, right? So it is very important circuit where it is a brain of a computer, a microprocessor, right? Where we have the arithmetic, which actually comprises of this uh, circuit, right? And also the logic circuit. Okay, so that will be the things that we will learn in this chapter. So before we go into details, because this chapter is about the combinational circuit, and all of these circuit are actually the combinational circuit. So we need to understand what is the combinational circuit at first. So uh, basically, the combinational circuit is a digital circuit in which the output value depend on the present combinational of input values. Right, so that is the definition. So to understand this, we can have a module or circuit in a box like this. All right, if this is our module or circuit, so we will have a set of input. For example, A, B, C, D is our input, and then we have output. All right. So combinational circuit means that the circuit that if any of the input here change the value, for example, from 0 to 1 or from 1 to 0, it will immediately affect the output here, right? So that is meant by this statement. So for example, if we have something like this, so if input is 0, 0, 0, the output F is of course 0. And when C change to 1, F will immediately change to 1. All right. So that is meant by combinational circuit. When the input, any of the input change, it will affect immediate F. Right. it will immediately affect F. So in digital circuit, we will have another kind of circuit. We call it sequential circuit. Yeah, it's the digital circuit with the output value depend on the present value and the past input values. All right. So this is the second kind of digital circuit. Yeah, we call it sequential circuit, where the output value is not only depend on the present input value but also the past input value. Meaning that if again this is the sorry. So again, if this is our circuit, now if this is the sequential circuit, so the output here not only depend on the present input value but also depend on the past value of this, right? So for example, if the input value is the current input value is 0, 0, 0, E equal to, this is A, B, C, D, and you have E here, E equal to 0. And when D change to D, D change from 0 to 1. So maybe the output change to 1, right, for E. Okay, so this is one example. But if, for example, if the previous value is this, and now we change to 1 also, this is the same, right? You can see that this is the same. If the combinational circuit, if this is the combinational circuit, so what happened is that the output should be 1, right? Because this will give this. So this also will give this. But for sequential circuit, yeah, the output, the present output value here is not only depend on this, but also depend on the previous input value, which is this one. So you see here, the previous value of this one and this one, this case and this case, is different. So before the input change to 0, 0, 0, 1 for the case 1, so let's call this case, this is case 2. So for the case 1, the previous value is 0, 0, 0, 0. And for the case 2, the previous value is 0, 0, 1, 0. So the output here is not necessarily equal to 1. It can be 0 because of the previous value of the input. So this behavior, or the circuit that have this behavior is called a sequential circuit. Right. So for example, the sequential circuit, the example of sequential circuit is latch, flip-flop, register, finite state machine, FSM, memory. Right. All of these are the sequential circuit, and we will learn this in chapter 4. All right. So remember, we will have two kind of digital circuit. The first one is the combinational circuit, and the second one is the sequential circuit. And both type of circuit is very important in digital system where they are the basic block to develop the complex digital circuit. All right. So if you have a complex data circuit, so inside that data circuit, you will have both of the circuit, which is the combinational circuit and also the sequential circuit. All right. For example, if you look at the circuit in the microprocessor in the computer, so it will comprises of that sequential and combinational circuit. So for example, this is the example. Logic gates, it's the combinational circuit. Multiplexer, combinational circuit. Decoder is the combinational circuit. Register, basic register is the sequential circuit, and controller is the sequential circuit. Okay, so in this chapter, we will focus on the combinational circuit. So let's look at the first combinational circuit that we've actually familiar with, yeah, because this one was introduced to you in the first chapter and the second chapter already, which is the multiplexer, right? So multiplexer is a very important circuit in the system where it is used to isolate signals, right? So for example, if we design a complex circuit, so for example, a computer system, right? So most of the time, we share the same wire to carry the information or data, right? So for example, we have what we call a bus, yeah, a universal bus or common bus, right? So maybe we have many devices or peripherals that need to use this bus in order to communicate with other peripheral. Okay. So for example, this is the output port. For all of these peripherals. All right. So all of the time when you power on your computer, so there will be data in this wire. For example, this is an 8-bit wire, and the bus is 8-bit also. So there will be data or signal in the wire. All right. And when we connect this wire to the bus, and this one also connect to the bus, and this one also connect to the bus. So what happens is that the signal here will interfere with this signal and also this signal. All right. So that will make your data corrupted. So we don't want this to happen. So what we do is we need to isolate this, and we need to just only allow, yeah, at one time only allow only one peripheral to access the bus, right? So what we do is that we have something like this. Instead of directly connect all the peripheral to the bus, now we have the multiplexer such that
at one time, only one signal here can send the data, one peripheral here can send the data through the bus, right? And of course, we need to have the select input or control input here to select which one can access the bus here at a time, right? So that is the use of multiplexer, and we will use this a lot later on in our design, right? So the multiplexer that we have now here is the what we call the 2-to-1 multiplexer, right, where we have two input and one output and one control signal. And this is the behavior of this multiplexer, where we can see here, if S equal to 0, the output will be equal to W0. See here, if S equal to 0, the output F here will be equal to W0. And if S equal to 1, the output F here will be equal to W1. Right, so that is the behavior, and we can derive the truth table for this behavior like this, where we have two input and one select input. So in total, we have three input S, W1, W0, and we have one output F. And we can see that here that if S equal to 0, F is now equal to W0, 0, 0, 1, 1, 0, 0, 1, 1, see? But if S equal to 1, what we have here, F is equal to W1, 0, 0, 1, 1, 0, 0, 1, 1, right? So that is the behavior. And from that behavior, the truth table here, we can derive the logic equation. And also we can derive the logic circuit, all right, from here. So this is the circuit of the 2-to-1 multiplexer, which is very straightforward. And of course, when we have the logic equation like this, we can describe the the multiplexer using data flow modeling. And also we can describe the circuit using the structural modeling, because we have the schematic here, right? In this example, I use the behavioral modeling, where see, use the always block, yeah, and here is the module name, mux 2-to-1, and we have the port W0, S, and W1, and we have F. Input is this, output, and also this declare F as rect. Why? Because F is a variable inside the always block. This is why F must be declared as rect as well. Okay, so the description is very straightforward. If S equal to 1, so if S equal to 1, the output is equal to W1, else the output F is equal to W0. That's it. So this is a 2-to-1 multiplexer, which is very straightforward. This is another multiplexer, which is the 4-to-1 multiplexer. And this is the graphical symbol of the multiplexer. And for 4-to-1 multiplexer, we need two wires for the control or for the select input, right? Because one wire is not enough, because one wire we only have 0 and 1, so we can represent only two option, right? But if we have four possibilities like this, so we need to have two bit or two wires for the control, such that we can have 0, 0 for W0
01 for W1, 10 for W2, and 11 for W3. And this is the truth table, the simplified truth table, yeah, like this one, right? The full truth table is not given, so you can try to derive, yeah, from this simplified truth table. Okay, and this is the structure of the 4 to 1 multiplexer. Okay, where uh, here this line is actually W0, S0 bar, S1 bar, so you have this and so on. Okay, so here you can also describe using data flow modeling if you have the Boolean equation. And of course, if you have the structure like this, the schematic like this, the circuit like this, so you can describe using structural modeling as well. And in this case also, I use the behavioral modeling, right? Now, the interesting part is that the input here, W is 4 bit, right? So we can write like this, yeah, to represent 4W. Means that W we have W0, W1, W2, and W3, right, in the form of vector like this. And S also we can have in the form of vector like this. So we have S0 and S1. And the output, of course, need to declare as rect also, and have only 1 bit, so we don't have vector. And in always block, we can use what is called a case statement, right? So what is case statement? Case statement is actually same concept with the case statement in computer programming. For example, in C programming. So this is actually an if-else statement. If you have many if-else, yeah. For example, if you have if A equal to this is pseudocode, yeah, this is not a Verilog code. If A equal to 0, 0, so this is a statement. Else, if A equal to 0, 1, this is the statement. Else, if A equal to 1, 0, this is the statement. And the last one is else, means that A equal to 1, 1, right? This is the statement. So if you used if else like this is actually the same same thing, right, as the case statement. So if we have many conditions like this, yeah, we want to test many conditions like this. Yeah, A has, for example, 4 conditions: 0, 0, 0, 1, 1, 0, and 1, 1. So we can use if else, if again, right, until we have all the condition. But the best way to test A is to use case statement, right? So this is the example of using case statement. In this case, we test S, right? So of course, because S is 2-bit, so S can be 0, 0. So this is how we write, yeah, 2-bit in binary 0, 0. So if S equal to 0, 0, F should be equal to, yeah, exactly based on this, W0. If 0, 1, F equal to W1. If 1, 0, F equal to W2. And lastly, if S equal to 1, 1, W equal to W3. Right? So this is exactly based on this behavior or truth table. Right? And case
Yeah, you need to have end case, end case, and of course end module to end your module, to end your design. Right, so easy. And this is another example of designing 4-to-1 multiplexer, but in this case we used the previous design, yeah, which is the 2-to-1 multiplexer, to design a 4-to-1 multiplexer. And remember, this is called hierarchical design methodology, where we reused the previous design to create a larger design, right? So it looks like hierarchy here, where we have a small design at the bottom, and we connect together that small design to create the bigger design, right? So the small design in this case is the mux 2-to-1, and the bigger design that we want is the mux 4-to-1, right? So here we can have our module name. This is mux 4-to-1, a new name. We have input W, we have S, we have F, and of course our W is 4 bit, yeah, 4-to-1, remember, and we have 2 bit for control, S, we have 1 bit for F, and we have wire here, Y. So why we need this wire? Because to use hierarchical design methodology, we need to describe using the structural modeling, right? And this is what we call the module instantiation, right? So if you go back to chapter 1 here, chapter 2, sorry, here, right? We have gate instantiation and this module instantiation. So here is actually the module instantiation, means that we import our previous design or another module to our current design, right? So that is module instantiation. So to import, we just call or put the name of our previous module, which is the Mach 2-to-1, this one, Mach 2-to-1, right? And we give a name for each module here. So in this case, this one we call it Mux. This is Mux 1, and this is Mux 2, this is Mux 3, right? And wire, of course, when we want to describe the circuit using structural modeling, so we need to have a wire name. So because this is the internal wire, so we need to give it a name. So this one we call it Y0. This one we call it Y1. Y0, Y1, right? So that must be declared as wire, right? So we have 10 or 01, doesn't matter in this case. So how to do the connection? So this is how. So to describe Mux 1, which is this one, so we need to do the connection here. And remember, to do the connection here, we have two methods. All right, remember in the previous chapter also, we have two methods. Let's go back, go to here, right? Hierarchical design methodology. Yeah. This example, we have two methods of port connection. First is we call the name port connection or port name connection syntax. The second one is called positional port connection syntax. So what is the difference? The difference is this. for port name connection syntax, we need to use the port name to connect to each other. All right. So, for example, uh, we want to, connect this A to this A in our previous module. So what we need to do is dot A. Yeah, this is dot A bracket A, means that this one is connected to this one. This one dot B connect to B, right? Yeah, B, and so on. But the second connection method is positioning port connection syntax. By using this one, we don't need to connect like this, A to A. We just use the position of the port. So for example, M1 here, this is M1. We want to connect this A to this A. We should know that this one, where is the position of this one in the port declaration in the port list in the small design. So in our case, yeah, in our case here, A is the first one, followed by B as C. So here, A is the first one, followed by B, so need to connect to B. As here, need to connect to W1, so we have W1. And C need to connect to W3, so we have W3. Same as M2. So the first one is this one, connected to CI. That's why we have CI. Here connected to W1. All right, because the second port is B. So we need to have W1 here. The third port is S. So need to connect to S. And the last one is C. Connect to W2. That's why we have W2, right? So that is port positional syntax. So in this case, here we use port positional syntax, not the port name connection syntax, right? So the position. So we need to look at the position of this port, yeah, the order of the position here. So we need to go back to see here. Oh, the first one is W0 followed by W1. So in this case, yeah, so should be W0, W1, right? W0, W1. What about this? S and F, right? W0, W1, S and F. So in this case, should be S0 for S. F should be Y1. So this is wrong. I label it wrongly. So I want to change this. This is not Y0, but Y1 in our case. This is Y1. This is Y0. Okay. So that S here is actually connected to Y1. Right? That's why we have Y1 here. And look at the second multiplexer. So this, yeah, according to this position, W0, W1, SF. Remember that. So it should be W2, W2, W3. This one is S0, S0, and the output is Y0, Y0. That's it for Mux 2. What about Mux 3? Mux 3 here, is y1. That's why we have y1 here. Here is y0. That's why we have y0. And this one is S1. S1. That's why we have S1. And the output is F. So we have F. So this will create this circuit. And of course, this circuit will have the same behavior as this one, right? Same as this one. And of course, the circuit is different, yeah, in terms of structure, but the output, yeah, the behavior is the same. Okay. So remember, we can describe our circuit in 3 different Verilog modeling style. Yeah, the data flow modeling, the behavioral modeling, and the structural modeling. So which one you want to use, up to you. All right. So that is the multiplexer. Now, the next combinational circuit that we want to look at is the decoder. So, so what is the decoder? So, the or we call it binary decoder, yeah, is a combinational circuit that convert a binary value to a set of signals, right? So this is the graphical symbol, and this is the general graphical symbol of the decoder, where we have n input here, and we will have 2 power of n output here. So for example, if n equal to 2, so the output must be equal to 4, right? And if input equal to 3, n equal to 3, if you have 3 input, so your output must be 8, something like that, right? And we have another input, we call it enable input. So this is not compulsory. Sometimes you need to have this, sometimes you don't have, yeah, depend on the design. So if you have enable input, so this enable will enable the decoder, means that if the enable is not active, the output will be equal to 0. But if enable is active, so the output will depend on this input, right? So let's look at the behavior of the very basic decoder, which is the 2 to 4 decoder here, right, where we have 2 input and 4 output, and we have 1 enable input. So this is enable input, en, and we can see that if enable equal to 0, so it doesn't matter what is W1 and W0, we don't care, the output will be always equal to 0, right? So that is the enable. But if enable equal to 1, now the output here will depend on the combination of W1 and W0. So if W1 equal to 0, W0 equal to 0, Y0 equal to 1. The rest equal to 0. And if W1 equal to 0, W0 equal to 1, Y1 equal to 1. The others equal to 0. 1, 0, Y2 equal to 1, others equal to 0, and 1, 1, y3 equal to 1, and others equal to 0. So this is the pattern. So you can change the pattern up to, actually it is up to you, up to the design, but this is the common type of decoder that we have. Yeah, so you can have the logic circuit also based on this, because this is quite straightforward to derive the logic circuit, right, based on the sum of product, right, where for example y0, you can have y0 equal to 1 if en equal to 1 and both w1 and w0 equal to 0. So you can see that en here and both w0 and w1 equal to 0, not w0 and w1, so you will have y0 same as y1, y2, and y3. So based on this, so it should be straightforward. And the application, yeah, of the decoder is including data the mux, yeah. So we can use decoder as the multiplexer also. And the most common application in data system is this memory addressing decoding, right? So it is very important in computer system, especially when we want to decode the address, yeah, of the memory. So maybe I can uh, give you example a little bit on this, yeah, how the computer work, right? So in a computer system, yeah, so you will have a memory, and normally the size of the memory is for one location we can store 1 byte data or 8 bit, yeah. So this is called 1 byte. And in memory you have many locations that each location can store 1 byte data. And in order to access the memory, for example, the microprocessor, right, want to read the data from the memory or want to write the data to the memory. So it need to access using what we call the address. So the memory has a unique address. For example, location here, this memory location, the address is address 0, and the next is address 1, address 2, 3, 4, and so on, right? So for example, if we have 4 gigabyte 4 GB memory, so it will be addressed from address 0 until address 4 GB, gigabyte, 4 billion byte, right? Which is very big. And the address is unique. So in order for microprocessor to access the memory, it need what we call a memory address decoder. All right. So for example, if the number come to the microprocessor is 000, means that want to access memory number 0, 4 bit. 4 GB actually 32 bit, you need 32 bit. Yeah. But for this, let's assume that the memory address is 4 bit. So you need to have a decoder in order to decode this address and activate this location or bring your microprocessor to this location. And if number 0001 come, it will decode to address number 1 and so on and so forth. So that is the use of the memory decoder, all right, or use of the decoder in the real application, right? So this is how we describe the decoder in Verilog. Okay, so we have the truth table, and if we have truth table, actually we can describe straight away using behavioral modeling, yeah, because the behavior is there, right? Okay, if you want to describe using data flow modeling, you need to derive the Boolean equation first. If you want to describe using structural modeling, of course you need to draw the circuit. Okay, but here because we have the truth table already, so we can straight away describe the circuit using behavioral modeling. Okay, so this is the example. So we have module. The module name is 224. This is 224 decoder. En, W, Y, the input. We have En, we have W input, we have Y output. Here we describe the input and output. So input we have W 2-bit 1 0, right? We have W1, W0. Input EN 1 bit EN. We have output Y, which is 4-bit. We have Y0 until Y3, so we can write like this 0 to 3. And we need to have rec as well, because Y, we can see here, is a variable, and it is inside the always block. So Y must be declared as rec as well. Okay. Now we describe using behavioral modeling or behavioral code. So always, yeah, this is the sensitivity list. Yeah. So Y is sensitive to these two signal, W and EN. So if EN equal to 0, yeah, this is how we write if EN equal to 0. So we can have two style of writing, right? We can have if EN equal to 0, or we can just write right. This is same thing. So if En equal to 0, yes, based on this, if En equal to 0, we don't care any other things. Straight away, Y must be equal to 0. And Y is 4-bit. Yeah, that is why we write like this. 4 B 0 0 0 0. All are 0. And this is Y0, Y1, Y2, Y3. Okay. And if En not equal to 0, or else here, means that if En equal to 1, so we will look at W. All right, and W we have 4 conditions. So the best way to have 4 conditions is that we use case statement, right? So this is how we use case statement. So case W equal to 0 0. So we have Y equal to this exactly, right? 4-bit 1 0 0 0 1 0 0 0, and 4-bit if 1 0 1 0 1 0 1, we have this. 1 0, we have this. 1 1, we have this. And case here, and module. So this will create the 2 to 4 decoder for you. And you can have another style of Verilog code, yeah, where you can do something like this, and it will give the same result, yeah, same circuit and same result, right? So this is how. So the input is the same, okay? Always here is different, okay? So here we can see that we don't have this, yeah, we straight away using case statement, and here we combine these two signal En and W to be 1, right? So now these are 3-bit, En 1-bit and W 2-bit, right? So if we combine, this is called the concatenation, right? Again, when we go back to chapter 2, yeah, this is concatenation, right? So concatenation is to combine the signal. So means that we combine En and W into 1. So this is what we do. Okay, we have En, which is 1-bit. We have W, which is 2-bit. And then when we write like this, So now we have a new signal, and this En and W become 3-bit. Okay, such that we can do something like this. Yeah, case 1, when En and W equal to 100, which is this one, 100. So Y equal to 1000, Y equal to 1000, 101, 101, this, 110, this, 111 is this. And the others, in case statement, when we want to describe the others, others from this, so this we have already, but other than this, for condition, we can use default, default statement. So this default statement is actually a Verilog keyword also. So you can use default y equal to 0. Right, means that other than this, means that in this case, this case, y should be equal to 0, 0, 0, 0, and case and module. All right, so that will give you the same result, the same circuit, right? But with two different coding style, not modeling style. Modeling is still the same using the behavioral modeling, but this is coding style. All right. So the interesting about the hardware description language or any computer programming language is that you can have different code, but still produce the same output, right? So actually, it is good for online learning, online examination, right? Because I can easily spot, if you copy from your friend, the answer is from your friend. For example, your code is 100% same as your friend's code, right? So that is only one possible, meaning that you copy from your friend, right? So remember, to learn this, to understand this, so you need to have your software, and you need to start to write your code. Okay, so in my notes, there are a lot of examples. For example, this one, right? So you can copy, always copy and run this code in quarters. Try to synthesize this. Try to simulate and see the output, the result, right? And whenever you start to code, okay, I can guarantee that you will face problems. Right, coding problem means when you compile your design, you will have maybe a lot of warning, maybe a lot of errors, right? But that is actually very good. It's good because whenever you encounter that kind of problem, you start to, or you need to figure out what is that problem means, right? And you will learn how to debug your program. And when you are able to debug your program, and you manage to solve all the errors, so it will make you understand the things that you want to do better, right? That is the things that actually you need to do, to learn this course. Okay, so that will be the decoder. Another decoder is the 3 to 8 decoder, right? This is 2 to 4, and we have 3 to 8 decoder, and this is the truth table. And you can also create the 3 to 8 decoder using two 2 to 4 decoders, right? So this is the 2 to 4 decoders that we have created here, and we reuse again here, and the connection be like this, all right? And we can have the 3 to 8 decoder. And also actually we can use the behavioral modeling, yeah, means that using this style of coding, and we're not using the previous design based on where we design our 3 to 8 decoder based on this truth table, yeah, not using the previous design. So this is how we code if you want to use the previous design. So again, this is 3 to 8 decoder. We have W input, we have EN, yeah, we have Y output, and Y is now 8-bit, right? So you can see that W is 3-bit, 2 to 0. We have W2, W1, and W0. We have EN. Output, we have 8, yeah, from 0 to 7. And we have wire Z, right? So we have Z1 and Z0. So again, this is Z1, this is Z0. So Z is the output of this gate. Z1 is output of this gate. Z0 is the output of this gate, right? So to describe Z1 is easy. You can use the structural modeling or data flow modeling like this. This is data flow modeling, right? Z1 is equal to, yeah, for data flow modeling, you need to have this assigned keyword, right? So Z1 is equal to W2, not W2. So here, not W2, and EN. So this is N, EN. So you have Z1. And you have Z0 is EN and W2. EN and W2, or W2 and EN, right? So you have Z0. And you can do the use the structural modeling here, where you need to instantiate the 2 to 4 module here. So this is 2 to 4 module. You instantiate, call it again. Let's name this as DEC1. This is DEC2. So we have Z1. So why we have Z1 here? Again, we need to go back here, because in DEC2 to 4, the first port here in the list is EN. All right. So that is why we need to look at this EN. Now EN is connected to Z1. That is why we have Z1 here. And the next one is W10. What is this? W10. So again, need to go back here. We have W and W1, W0, right? So W here is actually W1, W0, meaning that here W1, W0. So here W1, one W0, or W0, W1, same thing. These two W connect to here, and the output Y here, but this Y is 3-bit, 4-bit, sorry. Y is 4-bit, 0 to 3. So in this case, this should be connected to Y0 to Y3. Yeah, Y0 to Y3. Done. Look at the second one. Again, the EN here is connected to Z0. So Z0 here. Here, same thing. We connect to W0, W1. So we have here W1 to 0. And look at Y here. Our Y here is connected to Y4 to Y7. That is why we have Y4 to 7 here. Now we get the same circuit as this one. Yeah. So it will create the 3 to 8 decoder for you if you code this way. Okay, so that is 3 to 8 decoder, and of course you will have a bigger decoder. So depend on how many input that you have. In this case, you have 3, you have 8 output. If you have 4 input, you will have 16 output. If you have 5, you will have 32 output, and so on, right? But you can do that because you can code in this style using behavioral modeling, all right? As long as you have the truth table. This is another example of the application of the decoder, yeah, the 7-segment display. So this is an old technology actually. 7 decoder is not using in the electronic that we have today already, but it is used in, for example, in traffic light, right? We have the 7-segment, still have the 7-segment, right? So this is the 7-segment decoder, the block diagram. So we have 4 input and we have the 7 output. So the 7 output is based on this. Yeah, this is the for example, the LED. So we have A, B, C, D, E, F, and we have G. So if number 0, for example, so we need to on A, B, C, D, E, F, right? And G should off. So the relation with the input should be like this. If 0, yeah, 0. So this should be 1 to indicate that this LED is on. This one is on, B is 1 until F, and G is 0. So that is number 0. What if the number is 1? 1 means that number B and C should be on. So that is why we have 1 1 here, B and C, right? And others are 0. Number 2, yeah, A, B, G, E, D. A, B, G, G, D, E, right? And so on. So this is the decoder also. So you see, if number 2, number 3, number 4, number 5, and until number 9. Yeah? So this one can represent from 0 to 9, right? And the code. So this is how we code. So we have input 4 bit, 3 to 0, and we have the output from 1 to 7, right? 7 bit, 1 to 7, and we can see that we can use case W, the input, yeah, and A, B, C, D, E, F, G equal to this if W equal to 0, if W equal to 1, equal to this, exactly based on this. But look at this. This is very important when we code in behavioral modeling, especially when we use case statement, right? Just like if statement, you need to have else statement, right? If, else. If you have if, but you don't have else, so what happens is that the Verilog compiler will create the memory element for you when you compile your design. Same as this case, yeah, because actually if you have W 4-bit, right, 4-bit like this, so the possible combination of the input or W should be from 0 to the last one should be 1 1 1 1 or 15, right? You should have 16 possible combinations, right? But because the 7-segment, we need only 9 from 0 to 9, so 10 combination, right? So the others is not represented here. So in Verilog, it is not recommended. So what you need to do is you need to have default. Why? Means that other than this 0 to 9, so we don't care. All right. So this is how we create the circuit using behavioral modeling. Right. After this will be the encoder. Okay. But before the encoder, maybe I want to do the demonstration, yeah, to write this code in quarters and try to simulate the code such that you can learn how to use the software,
yeah, and how to use the node and this node in to learn how to use the software to code to write the code to compile, to write the test bed, and to simulate the design. Yeah. Okay. But before that, maybe we have a short break before we continue to the quarters demonstration.